Hey everyone, thanks for coming to the talk, and yeah, sorry about the delay and the technical difficulties. So I'm Nisha Johnson, Product Manager for Ray on GKE at Google Cloud, and this is Ryan O'Leary. I'm thrilled to be co-presenting with him. We're essentially here today because we believe that Ray and Kubernetes work really well together. Kubernetes is the open source standard for platform builders. It gives you hardened orchestration at scale, and Ray is really the open source standard for distributed applications. It has a great Pythonic API. And our goal with this presentation really is to show you how you can combine these two platforms together to create an efficient platform for your teams and for your AI workloads. Now, building this platform comes with its own challenges, and we've identified 5 key challenges here. And the first one is access. Before you even start building your platform, you need to think about choosing the right accelerators, you need the right GPUs or TPUs, and you need it when you need them. The second challenge really is on the performance side. Once you get the accelerators, you're juggling things like new models and algorithms and optimizing for different hardware types. You also have to then, on your massive investment, ensure that you're maximizing efficiency and making sure that your developers are productive and able to use the investments you've made into your infra. You also have to make sure that it's usable. You're juggling all kinds of open source frameworks, hardware types, orchestration tools. So how do you make sure that they're all working well together and they're extremely usable, and it doesn't become a daytime job just to manage the platform? And finally, of course, you have to ensure security. Things like appropriate access controls and safeguards. And today we're going to show you how we're working to fix the challenges at all these 5 levels, through improvements on the Ray side, through improvements on the Kubernetes side, and through improvements on the GKE side. So let's start with the first challenge, access. Access means having the right hardware for the right job. And Google Cloud offers a wide variety of options on the TPU side and on the GPU side. So if you're doing low-cost inference, that might look like requesting L4s. If you're doing frontier model training, that might look like choosing a V6E or a V7E TPU. And one challenge, of course, is identifying, how do you map your workload to the right hardware type? But the second challenge is how do you get the compute when you need it? And so how do we help you secure that capacity? And so this is why we built Dynamic Workload Scheduler. Essentially, what it does is it gives you a flexible way to access the compute you need when you need it. And so there are 2 ways to use Dynamic Workload Scheduler. You can use Flex Start for things like jobs that run for up to 7 days. It is a pay-as-you-go model. You don't need to have any sort of fixed reservation. And what it allows you to do is quickly start with any experiments you have, short-term jobs like fine-tuning or batch inference. And let's say that you wanted a job, you wanted compute for a job that was a little bit more long-running, and you needed slightly more guarantees as to when it would start. You would use something like calendar mode. And with calendar mode, what it does is it gives you a short-term reservation. It's kind of like booking a hotel or an Airbnb. It's a future reservation. It can be as long as 90 days. You kind of have to pay up front for the full reservation, so it's not pay-as-you-go, but it still is a guaranteed mode, and you don't have to be tied into a year-long or a multi-year contract. And so, okay, now you have decided on the compute that you want. You've secured it. But let's assume that you have to share these resources with multiple teams. And you have now this problem of multi-tenancy. And so let's assume that there was a team that was using the reservation that your company got and the compute that you have, and another team wanted to use the compute or start a job. So how would you deal with that? And that's where we introduced something called Custom Compute Classes. And with Custom Compute Classes, essentially what it does is it makes your jobs more resilient. And so essentially, this is an example of, let's say, someone who wanted to start off a job with an H200 reservation. Unfortunately, another team was using it. And so with custom compute classes, they would define in the YAML file what their fallback options could look like. So they would say, first try to get that H200 reservation. If that doesn't work, fall back and try to get one of those H100 DWS flex starts that my team has. If that doesn't work, try an H100 spot instance instead. And so what's really interesting and really powerful, and something that Ryan will share in a bit, is that your developers, the ones who don't like YAML and the ones who like to stay within Ray and Python, can get this fallback logic directly from the Ray code. And so custom compute classes help teams share resources effectively. But there's still another problem, especially if you're dealing with multi-tenancy. So let's say team A was using all of the resources in the reservation, but team A wasn't supposed to. Or if both team A and team B requested a job at the same time, who goes first? And so there's this issue of prioritization that comes into the picture. And so that's where we have a solution called Kueue, which is a Kubernetes native queuing system. And what it does is it allows you to set quotas for different teams. You can do resource sharing. You can preempt lower priority jobs. You can also do things like more intelligent FIFO. So it's not a simple whoever comes in first gets the compute first. It even has intelligence built into it. For example, if there's a lower priority job, that can get started quickly because it just requires fewer compute resources and it's available. Kueue would allow that job to go ahead first. So now I've showed you a little bit about what solutions we have, but now my colleague Ryan is going to show you how all of this comes together in an example.
So since we're talking about how to achieve peak performance with Ray and Kubernetes, it's important to quickly introduce Kueue to those of you who might not be familiar with it. So Kueue is a powerful open source operator that simplifies the deployment and management of Ray applications on Kubernetes. It handles the creation, deletion, and reconciliation of pods to run your Ray nodes on. And it provides some really useful custom resources like Ray clusters, Ray jobs, and Ray services, the latter two of which streamline the deployment of jobs and serve deployments respectively on your Ray cluster instance. When running on GKE, we provide a managed Kueue operator through the Ray add-on, which you enable in your GKE cluster. Enabling the add-on installs the operator in your cluster, handles log collection and observability in Google Cloud Monitoring, and additionally installs some useful webhooks, such as one for configuring TPU pod scheduling and the runtime environment in those pods so that they can successfully initialize with JAX, since the JAX runtime requires some environment variables to be set when running on TPUs. Running on GKE provides a simplified experience for developers since you no longer have to configure all these different pieces yourself. So now getting into how we can bring these solutions together to create a unified scheduling experience on Ray and GKE that streamlines the complicated setup associated with running ML workloads on difficult to obtain accelerator resources that might be prone to quota issues. So for example, a realistic scenario might be that we have 6 teams at a company sharing some resource pool of compute, and they're all attempting to run jobs on ephemeral Ray clusters, and they're likely running into some capacity issues like stockout. So using Kueue to prioritize the different jobs, dynamic workload scheduler to get compute fast, and custom compute classes to specify node priorities and support multiple accelerator types like both GPUs and TPUs, we can help fix some of these problems. In the code example on the slide, we have what the end user experience might look like for a developer. On the left, we have a very simplified example where a custom training worker is decorated with a label selector and fallback options. The new label-based scheduling APIs are currently being integrated into libraries like train and serve, to where in the future, for example, you could pass them to your existing Torch trainer rather than having to write your full Python code using just the Ray core APIs. With the decorator, we'll try to schedule first to a v6e TPU group, and we'll fall back to v5e if that's not available. On the right, we have what their Ray job custom resource might look like. The key here is that through the Kueue label, we're adding it to gang schedule the pods in a local queue. We've also specified that we want the Ray job to run using a custom compute class for each node type, and we've configured each group with the relevant top-level labels fields for Ray autoscaling so that they're set in the Ray node runtime. Now we're getting into how the platform administrator might connect the pieces so that DWS Kueue and our custom compute classes and the Ray code that the ML engineer submits can all work together. On this slide, we're setting up the local queue and the cluster queue. For those not familiar with Kueue, we're essentially just setting up one shared resource queue that defines the types of accelerators we have available on our actual GKE node pools. The local queues should be set up in their own namespaces for resource and security isolation and are used by each team to submit their jobs. When we submit a Ray job with pod containers that request google.com/TPU to our local queue, we'll be routed to that flavor in the cluster queue and try to obtain those resources from the shared pool. Next, we have the custom compute classes. We're using these with our queue to define the specific types of accelerators and instances we want to try, and what to fall back on when the first option isn't available. So for TPU v6e, we'll try to first get the 2x4 on-demand node, and we'll fall back to a spot instance of the same topology if that's not available. In this scenario, we might prefer the more reliable guaranteed on-demand capacity, but we're willing to accept the cheaper preemptible spot instance if it can be acquired quickly. Conversely, for the v5e accelerator, we'll first try to provision the cost-efficient FlexStart instance with DWS of the same topology as the v6e TPU, but we'll fall back to an on-demand instance if that's not available and we just need to schedule it somewhere. So you might notice that we're specifying different fallbacks in our label selectors versus in our custom compute classes. This is because the label selectors only check for the labels that we've specified on each Ray node, which will then scale up a pod if found, whereas the custom compute classes specify the fallbacks to use so that the pod actually schedules somewhere in GKE. So it's kind of just two different levels of scheduling. Using both features together enables us to express a huge combination of scheduling options and fallbacks, which ensures greater reliability in a more streamlined fashion than using either API on its own. Finally, we define the resource flavors, which specify our custom compute classes respectively, and the admission check, which is referenced in our shared cluster queue. The admission check connects Kueue to GKE's dynamic workload scheduler, enabling Kueue to manage a queue for TPU-based jobs that require all-or-nothing provisioning. The resource flavors check for the custom compute class node selectors that we put into our worker groups, defining what's available in our cluster queue. Now that the platform administrator has set up all these different pieces to ensure that Kueue, DWS, and CCC are linked together, the final application code simply needs to specify a label selector or a fallback strategy that matches labels specified in the top-level field of our Ray custom resource. This ensures scheduling happens on the desired accelerator type or fallbacks, scaled up using Kueue and our GKE setup, and enabling more complex use cases for developers. So as you've seen through the features we just covered, Ray and Kubernetes offer powerful solutions for performance, utilization, and cost efficiency. However, different AI workloads, from training to serving to new agentic patterns, have different needs, as you can see listed under each group on the slide. And Ray on GKE gives you the tools like gang scheduling, accelerator sharing, and high availability to optimize the entire stack for each specific workload. We're also continually adding new features like label selectors so that developers can better utilize Kubernetes in their Ray workloads. This slide covers a newly introduced Ray util TPU library, which adds some helpful utilities for scheduling with TPUs. Specifically, it utilizes the new bundle label selector API to construct bundles that are scheduled atomically on TPU slices in GKE, avoiding worker fragmentation across different slices, since that would fail to utilize the high-speed ICI interconnects that exist on that TPU slice and could cause workload hangups. So in this example, we just have a small task that we want to run on all the VMs in one TPU slice. And using the placement group, we guarantee that the created Ray nodes are running on the pods that are actually scheduled to the co-located TPU devices. Under the hood, this works by scheduling a task to worker 0 of the TPU slice and retrieving a unique name that gets set when running on GKE. If we're able to retrieve that name, then we know the slice is available, and we can create a placement group covering the whole topology. This enables SPMD workloads and is going to be integrated into libraries like RayTrain and Serve to orchestrate multi-slice workloads. One area that we've already implemented this logic is the new JAX trainer API in Ray. JAX is a Python library designed for high-performance numerical computing and large-scale machine learning that is often utilized in TPU workloads. The JAX trainer is the core component for orchestrating distributed training in RayTrain with TPUs. It follows the SPMD paradigm, where your training code is executed simultaneously across multiple workers, each running on a separate TPU VM within a slice. Ray automatically handles atomically reserving a TPU multi-host slice for you using the same logic we just talked about. In this example, we'll execute our training function across 4 workers in a 4x4 TPU v6e slice, and all the backend, like distributed setup, is handled by Ray. Now let's talk about serving. This platform simplicity extends directly to inference. You can use the exact same Ray serve and VLLM stack that you already use for GPUs, now on TPUs. For the developer, the experience is pretty simple. As you can see from the code, moving a VLLM workload from GPUs to TPUs is pretty straightforward. You just need to adjust the deployment config to account for the different shape of the device. This makes it easy to optimize for price and performance on the fly. The key differences to be aware of are that when moving between these two examples, we need to pass different arguments to VLLM, and we also need to handle the Ray cluster setup with an image that installs Ray and also the specific VLLM TPU dependencies, since it's a totally different set of dependencies and requirements than VLLM for GPUs. So make sure you follow the VLLM documentation on how to install a version for TPUs. Something we can hopefully do in the future will be able to provide an image or Docker file for users to install the latest version of Ray with a compatible VLLM TPU image. Finally, from the documentation from the Ray LLM config, it's marked as alpha. So when I was adjusting the example for GPUs on the left to use TPUs, I had to make some adjustments like explicitly setting the GPU bundle to 0, or we would add a GPU bundle. And so in the future, we're planning to continually improve this experience and reduce the amount of required adjustments you have to make.
Thanks, Ryan. So one other piece of the performance story is just startup latency, and that's especially important for serving. So if you have, for example, large multi-GB container images, pulling that image can take minutes. And this is why GKE image streaming used in combination with secondary boot disk is so critical. And what it allows you to do is allows your containers to start without waiting for the entire image to download. And this dramatically reduces pod startup time. And we've observed in internal tests that the time to mount a 16 GB image can be made faster by even as much as 29 times. And some of the sort of side benefits of this, apart from just the obvious pod startup, is that Ray autoscaling is also faster. If your pods get preempted or evicted, restart can also be faster. And so just overall performance is improved through the use of this feature. Once your pods are running and you've optimized your workloads, the next step really is, how do you optimize performance? How do you see what's happening inside your workload? And so that's why we've fully integrated TPU metrics into the Ray dashboard. It's also available for use in your custom Grafana or Prometheus dashboards. We also have metrics for Ray in general, both TPU and GPU, available in the Cloud Console if port forwarding is not something you want to do. And you can see essentially all the stats that you need to use for optimization of TPU metrics, like tensor core utilization, HBM usage, duty cycle, all of that in one place. And previously, all of this used to be an extremely opaque process for TPUs, and now you have that same feature parity if you're considering TPUs for optionality or price performance. And finally, let's talk about one other workload, the workload of the future, agentic AI. And with agents, there are a couple of challenges that make it difficult to move from prototype to production. And the solution is what we're calling the decoupled agent platform. Ray actually has a great architecture for how agents operate. So Ray actors offer a stateful brain that can be used for the LLM and the model that's actually deciding on the tasks to be done. And then you can use Ray tasks for the stateless tool calls. Now, when you use Ray and Kubernetes in combination, that's where the magic happens. So in addition to just using Ray for the orchestration, you may want to restrict your agent's sort of zone of control to a certain limit. And that's where we provide the secure foundation. We integrate very well with the gvisor sandboxes to provide kernel-level isolation. And this means that you can safely execute untrusted LLM code without compromising the host. And in terms of uptime and the user experience, you want to ensure that there is fault tolerance. Ray, as you know, has incredible fault tolerance that comes with GCS. But when you combine that with Kubernetes, you get KubeRay that can manage the entire lifecycle of the cluster. You can essentially auto-scale and heal if your nodes go down. And when you use Kubernetes in combination with other tools like Kueue, you can ensure that agent tasks are not fighting for resources and they're queued in priority. And so it's efficient, they get the resources they need to overall optimize performance end to end. And so if you want a deep dive on this topic, I highly recommend the talk, The Decoupled Agent. It's happening today at 3:15 p.m. at Yerba Buena 23. So wanted to also call out one thing. A lot of the work that you've seen today, from the TPU integration to the label-based scheduling, using label selectors to use custom compute classes without having to deal with the YAML, all of those features is the result of a deep and ongoing engineering partnership that Google has with Anyscale. And we're both truly committed to making Kubernetes the best place to run Ray. And so if you remember just 3 things from our talk today, I hope you'll make it these. The first one is that we're delivering unmatched cost effectiveness. And you can save costs with custom compute classes. You can get the compute you need, often at discounted rates with dynamic workload scheduler. And you can further improve efficiency and resource sharing with Kubernetes native queuing systems like Kueue. You can use Ray and GKE and Ray and Kubernetes as a platform for all your AI workloads, from training and serving to agentic workloads. And finally, this is a partnership-driven platform. The joint engineering between Google and Anyscale makes Ray and Kubernetes one of the best foundations for you to build your own AI platform. So we announced a lot today and shared a lot of features, and we have some blogs and documentation for you to get started. And I hope you'll check out some of these links to learn more. Thank you so much for your time, and Ryan and I would be happy to take your questions.
Okay, thank you, Nisha and Ryan. So if you have questions, please raise your hand, and I'm gonna give you the microphone.
Hello. How does Kueue interact with Ray in terms of implementing like fair share scheduling? Like, does it communicate with the Ray autoscaler such that like pods will or will not be created depending on which team or user is requesting that?
So Kueue has support for Ray jobs. So you can submit your Ray jobs into like the queuing system.
I see.
Yeah.
Hi, thanks for the talk. I was wondering if you could talk a bit more about the image streaming. I'm not sure if I got that, because I've definitely run into the problem where the pod startup time is too large because of CUDA images. Is that something on the GKE platform, or what's the solution?
Yeah, so image streaming, it's a simple flag. When you're creating the GKE clusters, it's -- enable image streaming. And you can use that in combination with secondary boot disk if you have large models as well. And the way it works is it gets your pod from pending to running and ready much faster by streaming the contents of the image and sort of intelligently deciding which ones you need as a bare minimum to get your pod running, and then as incrementally just streams the image in. And so that's essentially how it works, if that makes sense.
Cool. Any other questions? All right.
I'll come this way. Yeah, I was curious. For the TPU, is any way that we can do like a pipelining, or any way like to when we batch like a set of tasks and to utilizing because the CPU to like a TPU's memory copy, and those could be expensive. And is there any way to like preempt only partial of that when that small test is done, and then swapping the other one, but while the others are all in processing in TPU? Just curious. Thanks.
It was your question about like data transfer between CPUs and TPUs?
Yeah. So basically, to fully utilizing the TPU's resources, when you schedule like a batch, so is there any like optimization, like a bin packing for the TPU's memory utilization, where you can swap only a small piece when it's completed, while the others are still in progress, or things like that?
Well, I mean,
or have to be in a single batch, like all in and all out, all in, all out, like that.
so I mean, on streaming mechanisms, I believe that you could write like your own like custom kernels, but I'm also happy to like find you more resources afterwards. But we have something called like Palace kernels if you wanted to optimize like the compute communication path a little better, and I believe that it does offer options for like flexible data transfer between CPUs and TPUs. I'm happy to talk more after the session, yeah. Yeah.
Cool. Okay, one more question here.
So how does the preemption work? Does the compute class like compatible with the workload priority class?
When you say workload priority class in Kueue?
Yes, yes. So
So-
basically that's another like a CRD to support different tiers.
Yeah. The custom compute classes work in some ways at a different level to Kueue, and it essentially, if you have access to like all 3 classes of resources and you're eligible to use those resources, you would set up custom compute classes separately from Kueue, if that makes sense. Does that answer your question?
That makes sense. So
Yeah.
basically these two can basically work together.
Yes, they can work together. Yeah.
Yeah, I don't think it'll try and utilize the custom compute class until Kueue actually has like taken your job to the front and is trying to schedule it, and then that's like when it'll go to the fallback for the CCC. So yeah, they work together, but just like kind of in, like one after the other.
Cool. We are at time now, so we're gonna pause here. If you have more questions, feel free to reach out to the speaker offline. Let's thank you our speaker one more time.